Welcome back to the deep dive. Today, we're jumping into, well, something huge. Thermodynamics. It's all about energy, heat, work, basically the rules that run the universe.
It really is fundamental. And it's a big topic, so we've leaned heavily on some excellent synthesized material research papers, articles, summaries. We should also give a nod to physics teacher Haka Veli-Torun, whose work summarizing these complex ideas was really helpful.
Absolutely. So our mission today, let's try and pull out the really critical, maybe even mind-bending facts about energy, how it governs everything. We'll start at the absolute bottom, temperature-wise, and go all the way to the ultimate fate of everything, sort of a cosmic speed run.
Okay, let's dive in. Where better to start than the ultimate boundary?
Right. Absolute zero. We talk about temperature all the time, but what does it really mean physically? What's the lowest possible temperature and why that specific number?
Okay, so absolute zero. It's a point where theoretically all particle motion just stops
Yeah.
completely. Atoms, molecules, no vibration, no rotation, nothing. It's the total absence of that kinetic, that movement-based thermal energy. That's 0 Kelvin, 0 K.
And the amazing part is how scientists figured out this number, minus 273.15 Celsius. It wasn't just pulled out of thin air, right? It came from watching gases.
Exactly. It's a fantastic bit of scientific thinking. Early researchers noticed something really consistent. If you keep the pressure on a gas steady, its volume changes perfectly linearly with temperature, like clockwork.
How linear.
For every 1 degree Celsius change up or down, the volume shifted by exactly 1273rd of whatever its volume was at 0 degrees C.
Ah, so they could just draw a straight line on a graph, volume versus temperature.
Precisely. They plotted that line volume shrinking as it got colder, and then they just extended the line downwards.
Yeah.
Mathematically, of course, to see where the volume would hit zero.
Where the gas would theoretically vanish.
Right. And that line hit zero volume at exactly minus 273.15 degrees Celsius. That became the fundamental 0 point, the anchor for the Kelvin scale.
And that's the scale scientists use because 0 Kelvin actually means zero thermal motion energy. It's universal. Just for context, for everyone listening, water freezes at 0 Celsius. That's 273.15 Kelvin.
And boils at 100 Celsius, or 373.15 Kelvin. Each Kelvin step is tied directly to the fundamental energy of motion in the universe.
Okay, so that sets the floor. Now let's talk about the energy itself that thermodynamics is tracking, this idea of internal energy. What does that stuff inside matter?
Well, think of internal energy as like the total microscopic chaos inside any substance. It's the sum of all the kinetic energy, the constant jiggling and bouncing around of atoms and molecules, plus all the potential energy locked up in the bonds holding them together, their structure.
So changing temperature, melting something, boiling it, that's all about changing this internal energy store.
Exactly. You're fiddling with that internal energy budget.
Which brings us right to the big one, the first law of thermodynamics. Energy conservation. We all learned it. Energy can't be created or destroyed. But if that's true, why are we always talking about running out of energy or wasting energy?
That's such a key point. The first law is just about accounting. It says the total amount of energy never changes, but says nothing about the usefulness or the quality of that energy.
Okay.
All the first law states is this. If you add heat to a system, that energy has to go somewhere. It either increases the system's internal energy, warms it up, changes its state, or the system uses it to do work on its surroundings, like pushing a piston. The books always balance.
So the energy isn't gone, it just might have turned into something less useful, like low-grade heat spread out everywhere.
Yeah.
Which leads us neatly to the second law. This one's about the direction things go in, right? The quality.
Precisely. The second law introduces the concept of irreversibility. It's the fundamental rule that says heat, on its own, only flows from hotter things to colder things, never the other way around spontaneously.
Yeah. Like you never see a puddle freeze on a warm day by sucking heat out of the air.
Never. And this natural directionality means you can't just convert heat energy entirely into useful work without some kind of temperature difference to make it flow. There's always a cost. You always lose some useful energy in the process. It degrades.
That's the energy tax you mentioned. It's why perpetual motion machines that run on heat alone don't work.
Yeah.
It dictates the arrow of time, really.
Absolutely. It's why things tend towards equilibrium, towards messiness, towards everything being the same temperature eventually.
Okay, so first law is accounting. Second law is direction and quality. Where do we see the first law, the conservation part, really flexing its muscles in the real world?
Yeah.
You mentioned the atmosphere. Adiabatic processes.
Yes. Adiabatic processes are a fantastic example. Basically, it's any process that happens so fast or is so well insulated that essentially no heat gets exchanged with the surroundings.
Yeah.
The heat transfer, Q, is zero.
So any temperature change is purely due to work being done.
Exactly. Think about letting air out of a tire quickly. Feels cold, right?
Yeah, freezing sometimes.
That's adiabatic cooling. The air expands rapidly, doing work on the outside air, but there's no time for heat to flow in from the surroundings to replace that energy. So the air uses its own internal energy to do the work, and its temperature plummets.
Okay, got it. Now scale that up to the atmosphere. A parcel of air rising.
Same principle. Air near the ground gets heated, becomes buoyant, and starts rising.
Yeah.
As it goes up, the atmospheric pressure drops significantly, so the parcel expands, pushing outwards.
Yeah, because it happens pretty quickly, it's adiabatic, no significant heat exchange.
Right, so that expansion work comes directly out of its internal energy store, and the result, it cools down, and remarkably consistently too.
How consistently?
For dry air, it cools at a rate of almost exactly 10 degrees Celsius for every kilometer it rises. That number comes straight from the first law applied to this adiabatic expansion.
That's amazing, just physics dictating the weather. Now, what about the reverse? Air coming down a mountain. Like those Chinook winds or the Foehn winds in Europe, they can be incredibly hot.
Perfect counterexample. As air flows down a mountainside, the pressure increases. It gets squeezed, compressed, again, often happening quickly, so it's adiabatic.
So now work is being done on the air by the increasing pressure.
Exactly. And since no heat is escaping, all that work energy goes directly into increasing the air's internal energy. Its temperature shoots up.
Which explains those crazy temperature jumps.
Absolutely. You can get temperature soaring, sometimes up to 40 degrees Celsius or even more, very, very quickly, melting snow, drying everything out. It's the first law converting work into heat dramatically.
And this isn't just mountain weather, is it? This layering of air temperatures is behind things like temperature inversions in cities.
Yes, that's a really important connection. An inversion happens when you get a layer of warm air, maybe it descended and heated up adiabatically, sitting on top of cooler, denser air near the ground.
Like a lid.
Pretty much. It traps everything underneath. Pollutants, smoke, smog. They can't rise and disperse because the warm layer blocks vertical mixing. Places like the LA basin are famous for this, unfortunately. It's atmospheric thermodynamics trapping pollution.
Okay, so from vast weather patterns, let's zoom into machines. Heat engines, cars, power plants. What's their fundamental job, according to thermodynamics?
Their job is basically to take heat energy from a high-temperature source, called the hot reservoir, T-hot, and convert as much of it as possible into useful mechanical work, like turning a crankshaft or a turbine.
But the second law puts a restriction on this, right?
A major one. Because heat only naturally flows from hot to cold, and because you can't convert it all perfectly, every heat engine must dump some waste heat into a lower temperature. Place the cold reservoir, T-cold. They fundamentally operate because of that temperature difference, T-hot to T-cold.
They're basically exploiting the natural tendency of heat to flow downhill, temperature-wise, and siphoning off some energy as work along the way.
That's a great way to put it.
Which inevitably brings up efficiency. How much work can you get out versus the heat you put in? There's a theoretical limit, isn't there? Sadi Carnot.
Yes, the brilliant French engineer Sadi Carnot figured out the absolute maximum possible efficiency any heat engine could ever achieve, operating between two specific temperatures, T-hot and T-cold.
And it doesn't depend on the engine's design, just the temperatures.
Fundamentally, yes. The ideal Carnot efficiency is given by the formula, 1 minus T-cold divided by T-hot. Remember to use Kelvin temperatures here, the absolute scale.
So let's say T-cold, the outside air, is 300 Kelvin, about room temp, and T-hot inside the engine is 600 Kelvin. The best you could ever do is 1 minus 300, 600, which is 1 minus 0.5 or 50% efficiency.
Correct. That's the cosmic speed limit for that engine. No matter how perfectly engineered, it can never be 50% efficiency between those temperatures.
And real engines, with friction and heat leaks.
Always fall short, often significantly short of that Carnot limit. But that limit itself, dictated by the second law, is absolute. You can't get 100% conversion of heat to work in a continuous cycle, ever.
This inability to be perfectly efficient, this unavoidable waste heat, it sets the stage for the really big, slightly unsettling idea, entropy. What is entropy, fundamentally?
Okay, entropy. It's often described as a measure of disorder or randomness. But maybe a more useful way to think about it, thermodynamically, is as a measure of how spread out or how degraded energy is. It's the energy that's no longer available to do useful work.
So, like, the concentrated chemical energy in gasoline is low entropy. highly organized, useful.
Right.
But after burning, the energy is still there, first law, but it's spread out as lower temperature heat in the exhaust gases and the environment. Much less organized, much less useful, high entropy.
That's it exactly. Energy naturally tends to disperse, to spread out, to move towards states that are more probable statistically. And the most probable states are almost always the messy, disordered ones.
Like the sock drawer analogy, it takes effort to keep it ordered, low entropy, but left alone, it naturally slides into chaos, high entropy.
Perfect analogy. It takes work and input of energy to create or maintain order locally. But the overall tendency, the universal drift, is towards greater disorder, greater entropy.
And this leads to some pretty profound conclusions about the universe itself, right? The so-called heat death.
It does. The second law, applying to the entire universe,
Yeah.
implies that its total entropy is constantly increasing, always going up.
So even though life creates order locally, building complex molecules, cities, computers,
We do that by expending energy and creating more disorder, more entropy in our surroundings. Think of the waste heat from our bodies, from power plants, from cars. We're exporting entropy. The net entropy of the universe always increases.
and the ultimate endpoint of that process.
It's a state of maximum entropy. A universe in perfect thermal equilibrium. Everything at the same, uniform, likely very low temperature. No temperature differences left to drive any processes, no useful work possible. Just tepid uniformity. And the heat death.
Wow. Okay, let's quickly recap where we've been. Started with absolute zero, the physical floor for temperature, defined by zero particle motion.
Then the first law. Energy is conserved, just changes form. The cosmic accounting rule.
Followed by the crucial second law. Energy quality degrades, heat flows hot to cold, entropy always increases overall. This sets the direction for everything.
We saw these laws in action with adiabatic processes in the atmosphere, rising air cooling, descending air heating up dramatically.
And in the fundamental limits on heat engines, defined by Carnot efficiency based purely on temperature differences.
And finally, the grand concept of entropy, measuring energy dispersal and pointing towards the ultimate heat death of the universe.
But there's one more quick thing, right? A third law.
Ah, yes, the third law. It's sort of a practical addendum. It basically says that while absolute zero, 0 Kelvin, is the theoretical limit, you can never actually reach it in a finite number of steps or processes. You can get incredibly, infinitesimally close, but never quite touch zero, another fundamental limit.
So we know the basement exists, but we can never actually open the door.
A good way to think about it. It adds a final layer of constraint to our understanding. And again, the source materials did a great job laying out this whole logical progression.
It really is amazing how these few core laws govern so much, from the mundane to the cosmic.
It's the bedrock framework for how the physical world operates. Energy, its transformation, its limits.
Okay, so to leave you, our listeners, with something to think about. Considering everything we've discussed, especially entropy and the unavoidable generation of waste heat from any process driven by temperature differences, here's a thought. Your body is a warm engine running in a cooler environment. Every single second, you are generating entropy. Now, think about a simple act like opening a window on a cold day to cool down a hot room. How much precious low-entropy energy are you simply dumping out into the universe, accelerating that tiny bit towards the eventual heat death just for a little comfort? Makes you think, doesn't it?